Sir, some of them have joined.
Okay.
So there are 22 people now, sir. So
Yeah.
if you want, sir, we can start off the session today.
Yeah. Maybe we should start today's class then. Uh, so I have shared a few files, actually a presentation file from which I'll be talking today. So uh, if you can download that in your machine, that would be easier for you to follow. I hope all of you have downloaded that. I have shared them uh, just before the class. I have shared them in the WhatsApp group. Okay. So
Yes, it is shared in the time series analysis group.
yeah,
So all of you are kindly requested to download it for the class.
yeah. So for if you download it, then it would be easier for you to follow the slide. And I have shared one data set and one code part. So if I get time, I'll demonstrate that part. So please download all three files and keep it in your system. Okay. So is my screen visible to everyone?
Yes, it
Yes,
is
sir.
visible, sir.
Okay. Yeah. So is it moving correctly, the screen?
Yes, sir.
Okay. Okay. So so far we only have seen basic time series analysis where I have or we have some variable which is recorded over time, and we want to analyze such data uh, which is a which comes up as a result of the measurement taken on that particular variable across time. So this is a simple univariate time series data, and we have seen what are the model for this kind of time series data. Actually, we have seen a very classical and the most widely used model for analysis of such time series data. If you may ask me that uh, are not there other models that are used? Yes, definitely there are other kind of time series model which may be appropriate for other kind of time series data, but the model that we have seen, which is the Sarima model, that is most widely used time series model. Now, we have seen how to identify the order of Sarima model, the order of the differencing, and how to fit the Sarima model. We haven't discussed about the fitting technique, but there is a statistical method for doing that. Basically, the software packages, they implement maximum likelihood method for estimation of unknown parameter. It is a standard technique of estimating unknown parameter from the data. And then based on the fitted Sarima model, we can do forecasting. However, uh, uh, as I have mentioned that there are other packages using which you can just simply give the data and ask the package to give you back the best possible ARIMA model. Uh, for those packages, the order of the ARIMA model, the order of the differencing, that part also you don't have to take care of. The package itself will take care of that. Actually, there is a criteria called AICC. It will minimize and check for which value of AI PDQ combination the AICC is minimized, and it will return you that particular model. And then also we have also seen that there are commands using which or functions using which we can do forecasting with that fitted model. Now that this part we have seen in our packages, and also we have seen that the same thing can also be done in the Jamovi also, just using simple clicks. And then we have seen another kind of forecasting algorithm. There we haven't discussed in detail about the model part, but only about the forecasting part, and we call it Holt-Winters forecasting method. So just like the Sarima based forecasting method, Holt-Winters forecasting method is yet another very classical and widely used forecasting method. However, in certain cases, it is evident that in short-term forecasting or not short-term forecasting, but the medium-term forecasting, sometimes the SARIMA-based forecasting gives better result than the Holt Winters method. And after that, we also have seen another forecasting method, which was referred to as the Prophet algorithm, and that is an algorithm developed by data scientists, the Facebook data scientists, Facebook data science team, and that also have a background statistical model. Actually, they use Bayesian statistical technique to develop the model. Using that model also one can do forecasting. So that means we essentially talked about three different kind of forecasting approach, and using all this forecasting approach you can forecast. But this is all about when you have only a single variable which is observed over time. However, in reality, we don't have single variable. Most often we don't have only a single time series date, a single variable associated to which we got the time series, but rather we have multiple variables under consideration, where one variable may be the most important variable, and the other variable that are also time series variable, but they have a auxiliary purpose, in the sense that we may not be interested in forecasting those auxiliary variable, but they have very important role to play in our statistical analysis. So in that case, we talk about the time series regression problem. For example, let me give you one example. Suppose you are looking into number of dengue patients. So that is a time series data. Now, associated to this particular time series data, a very important information is the daily temperature. Uh, the daily temperature, maybe daily maximum temperature or the daily minimum temperature, or you may consider the daily mean temperature or the average temperature. So that is again another time series. When you deal with the number of dengue patients data set, there our main objective is not to uh, forecast what would be tomorrow's temperature. Actually, that is again a question of interest to those who work in climatology. I mean, it is of interest to them, but we who are actually working maybe in the medical sector, for them, forecasting the temperature or forecasting the rainfall, that is not of the main purpose. Here, the main purpose is to identify how many dengue patients, what would be the probable number of dengue patients maybe after 3-4 weeks. And based on that, one may have to do certain kind of planning, that how to manage this much of patients. Okay, so that means from our perspective, we have two time series. One is the number of dengue patients on a daily basis, and we have another time series, which is the daily average temperature. Now, for our purpose, the daily average temperature time series, it is an auxiliary part. I mean, we are not interested in forecasting that time series, but we are interested in forecasting the number of dengue patients for next few days, or maybe next 1 month, for next 30 days, maybe. So in that case, there is one time series which is of primary interest, and then there is another time series which is of uh, secondary interest, which we call the auxiliary time series. So how to incorporate such time series in the statistical modeling? Of course, if you incorporate such time series, your model may give better forecast. So that's why it is important to consider them. So that means when you record such auxiliary information in terms of other time series, so you must work with a statistical model, or you must work with maybe mathematical model or statistical model. It must include that part also. So that may not be of primary interest, but that definitely have some role to play. So let us see how such a time series would look like. Typically, we have a single variable y. Uh, Yeah, typically we have a single variable y. This is the primary time series on which we are interested and which is measured at different point of time t1, t2, tn. Now we also have another auxiliary time series. Maybe this is a time series uh, that measures the daily uh, average temperature. Now sometimes it may happen instead of one auxiliary time series, we may have multiple auxiliary time series. Like we may have a time series that records uh, the daily temperature, that also records another auxiliary time series that records the daily rainfall, and maybe another time series which records something else. Okay, so that means we have a single time series of primary interest, and we have k such different time series which plays the role of covariates. So you have another one auxiliary time series which is measured across the same point of time. Then a second auxiliary time series which is again measured across the same point of time. Similarly, a kth auxiliary time series which is measured across this same points of time. So in this case, how one can create a statistical model. So you can create a regression model with this time series covariates like this. So what you do, you just include those auxiliary variable in your model, uh, like a regression problem. So this is like the daily average temperature. This is the daily total rainfall, and so on and so forth. And then our error term. Error means it is something unexplainable. So after you can explain the number of dengue patients by temperature, rainfall, and other influencing factor, there must be some other remaining factors. There must be some other remaining factor that has some influence on the number of dengue patients. So we collectively call all these other remaining factors. Now, among these remaining factors, there may be factors which are unknown to us, which is yet to be discovered. Now, uh, if we collectively call all these remaining unknown factors by a single term, we call it by the term epsilon t. So this is like the error term, or actually it's really not error. It is the unexplainable part, the part that includes all other factors. So although we often use the term error, uh, it is often referred to as the error term in the regression model, but truly speaking, sometimes it may happen that it's really not the error, but it's actually the other unexplainable factor on which we don't have any idea. So that's why we forgot to record them, or we forgot to include them in the model. Okay, but still those factors are playing some role in determination of the number of dengue patients that will uh, arrive in coming days. Okay. So in that case, this will give us a simple regression kind of equation, and some of these covariates also may be not really an observed covariates like temperature. Temperature is an observed covariate. So these values are uncontrollable. If you want T is denoting the temperature, it is of course uncontrollable. It is something uh, that is changing randomly. On the other hand, there's a possibility that some of these covariates may include not such random part, but it may contain some deterministic part. For example, consider this equation. So in this case, there may be certain covariates that contain the temperature of today, temperature of tomorrow, temperature of day after tomorrow. Similarly, there may be other covariates that contain the rainfall amount of today, rainfall amount of tomorrow, rainfall amount of day after tomorrow. But there may also be terms like this, which only include here the auxiliary variable only includes that today is the first day, then tomorrow is the second day, and day after tomorrow is the third day, like that. So it will just contain the time variable, which is not a random variable, but a deterministic variable. It will include that time variable in the form of a covariate. Similarly, it may also include not only the time variable, but certain transformation of the time variable, like the log t. So it may be appropriate. So that again uh, depends on the particular problem you are considering. Now there is a chance that this uh, mm, the the primary time series process that you are considering, that may also show some kind of seasonal pattern. So those seasonal pattern can again be included in the form of trigonometric function. Like we know that these are the trigonometric functions: sine function, cos function. These are all trigonometric function, and this trigonometric function will have such a oscillatory graph. So that's why they represent the seasonal pattern in any model. So you can also include them. These are again transformation of the time variable. So like this log is a transformation of time variable. Similarly, the sine t is also a transformation of the time variable. Similarly, is cos t. Now you can also add up sine 2t, sine 3t, that kind of term. So that will actually give you multiple seasonality. So there may be time series data where instead of a single kind of seasonality, there may be multiple seasonality. Like there may be one seasonality according to the day of the week. Then there may be one seasonality according to the month you are considering. So in such cases, there may be multiple seasonality in the data involved, and you can easily accommodate those things eh, using such functions. Okay, so that is how we can incorporate the trend part, the time trend part, and the seasonality part in this equation. Okay. Yeah. So multiple seasonality components with different periods may be included in this way in such a model. Now, this model is assuming that the error is independent. So that is a big problem. So
Sir,
yeah,
uh, when you say that we can include the trend and seasonality, it
right,
will be based on the distribution of the outcome variable. Is
right,
that right?
right. Yeah.
Not on the covariate.
No, not on the covariate. Yes.
Okay. Thank you.
So if you see that the number of dengue patients is increasing very rapidly, so that means you definitely have to include such a term there in the equation, because the temperature and the rainfall, they really don't show you a steady growth. I mean, temperature increase, then decrease, then slightly increase, then again decrease, like that. But if you see that number of dengue patients is keep on increasing, so that means you have to include such term in your model. So yeah, so you have to check the outcome variable, and based on that, you have to decide what type of formula you have to include. Like there, I have given one such formula. You may have to include some other kind of formula. Like you may have to include beta 1 t, then beta 2 t square. So it may happen. So you have to decide what type of form is appropriate for the data you are working with. Okay.
Sir, and when we
Uh,
say seasonality,
hmm.
uh, does the sign mean the upward curve and cos means the downward curve?
Not really. Both of them actually give periodic curve, but their starting position is different. Like for example, uh, now this is, yeah. So uh, so if you look into the curve of the sine function, so it should look like this. And on the other hand, if you look into the cos function, if you look into the cost function, it would look like this. So
Okay.
both will be showing alternating behavior, but the thing is that there one may be considered as a displacement of the other. Like if you shift the position of this, it may overlap with this function.
All right. So
Yeah.
if we see any kind of seasonality, is it a good idea to include both sine and cos, or
Yeah.
how should we go about it?
Yeah. So if you see that your data is like going like this, maybe. Yeah. In reality, you will never see this.
Yeah.
So if your data is going like this, then maybe only sine or only cos, that would be appropriate. On the other hand, suppose you see that your data, I mean, it's like superposition of two functions. So in that case, perhaps you will see such a strange kind of seasonal pattern.
Okay.
So when you see such a strange kind of seasonal pattern, uh, that generally indicate that there may be multiple such sine cos terms are involved, but that you have to carefully decide. I mean, just by looking into the graph, it is not possible to say how many such functions are defined, like whether only two such thing, or maybe you have to include this term also, like beta 5 sine 2t, then beta 6 cos 2t, like you may have to include them also. So that all depends on what type of seasonality you are observing.
All right, sir. Thank you.
Okay. Now the problem of this model is that we are assuming that the unexplainable part, or the part that involves the other factor, other unaccounted factor, like we have uh, yeah, we may have accounted for the daily temperature, we may have accounted for the daily rainfall, and we may have accounted for some other variables. But there may be some other influencing factor that we forgot to consider, or that the scientists are still not aware that there are certain unexplored factors. Now, all those factors will be entering into the model through this not epsilon part, which we often call error, we call noise, etc., etc. But as it is clear that this other uncontrollable factor, they will also be time series, right? Like suppose, for example, this is uh, mm, this is maybe that may involve uh, the something like the ultraviolet uh, UV rays, like ultraviolet radiation. Okay, so that may be some kind of influencing factor. So perhaps we don't have any idea how those factors play a role in the growth of this kind of virus, or the vectors that transmit the disease. Okay, so then this this ultraviolet ray, so the daily ultraviolet ray or the exposure to ultraviolet ray, so those things, they will also create a time series. Now, since they will create a time series, and this error part is uh, actually created by considering all these unaccounted time series, so it should also have some kind of dependence or autocorrelation in it. So that means if you look into the autocorrelation part of this time series, like it is expected that this will also show some kind of uh, dependence across time, this unaccounted part. On the other hand, we are modeling that as IID. So that means it is telling that whatever happening on today has nothing to do with tomorrow. So that means we are completely ignoring that their time series. So that may create a problem. Okay. So that may create a problem. So such an assumption that we are assuming that today's error has nothing to do with tomorrow's error. But that is not true, because today's error may contain lot of information about those unaccounted factors like ultraviolet and other things, ultraviolet exposure for today, and tomorrow's error contains similar such information for tomorrow, maybe ultraviolet exposure on tomorrow, and these two exposure may be connected among themselves. Like if it is more exposure today, it is bounded to be more exposure tomorrow also. So there is no sudden change. So then definitely they will be correlated. So how then this assumption that tomorrow has nothing to do with today is feasible? So that means it is not a correct assumption in that case. So in that case, if we work with such a simple-minded regression model, it will going to give us incorrect result. Okay. So as I have stated here, this model doesn't utilize the dependence across time in the error component, this part. So it is really not a time series model. So we can use the usual regression model to fit it. So we can just use some package, maybe package in R, or maybe something in those kind of softwares like Jamovi, SPSS. And we can fit a simple regression model and can do forecasting based on that. But in that case, the forecasting won't be good because we are not accounting for the factor that these errors are actually correlated, and the model I am assuming that they are independent. It is not true. It cannot be true. So that means a more realistic model is that if we assume that this error part is actually not IID, but that is following some time series model. And what are the time series model that we have seen? Now we have seen that there are many different time series model like AIR model, MA model, then ARMA model, then even more general kind of time series model like we have seen ARIMA model, we have seen SARIMA model. So you can consider such model for this error part. Okay. So that is what is stated here. So such kind of regression model, time series regression model, they have a name. They are called dynamic regression model. Okay. So what is the model equation? Now it is again very similar to the previous one, the usual linear regression model. But the only difference here is that this error part, we don't any longer assume that this error part is IID, independent and identically distributed, but rather we assume that this error part is a time series model, or error part is a time series data. And we assume the most general kind of time series model for that, SARIMA, PDQ, then capital PDQ. We already have discussed about how such model would look like. Yeah, so we assume that. So this model has a name. This is called the dynamic regression model. Now, how to statistically fit such model? I mean, there are certain technique of doing that. Of course, we can always use packages to fit this model and come up with the result. But what is the background mechanism? The mechanism is that suppose this epsilon t is a SARIMA model. So what is the meaning of that? That means, so let me show with an example. Suppose this epsilon t, let's consider something easier. Let's consider something easier, not SARIMA. Let's forget about the seasonal part. That way the equation would be easier. Now suppose I just consider something very simple, that it is ARIMA P1Q. So that means this error part, it is not really an ARMA model. So that means if you look into the autocorrelation part of this error part, it will be decaying very slowly. Okay, it will be decaying very slowly. It will decay, of course it will decay, but it will decay very slowly. So that means it is not an ARMA model, it must be an ARIMA model. And suppose for the timing, assume that it is an ARIMA model of order P1Q. So that means the small d is 1. So that tells us that if I take only one time differencing, only one time backward differencing, then this thing, this object, this will now be an ARMA PQ. Now, if we look into this, if we start with this epsilon t time series, and if we take transformation of this epsilon t time series to create this new time series, and if we draw the autocorrelation function of the new time series, we'll see that the new time series is decaying geometrically fast, rapidly. It is decaying very rapidly. So that means only one differencing is good enough. Had it been the case that only one differencing is not working, maybe you have to do differencing 2 times, 3 times, then of course it would be 2, this would be 3, like that. So that was the whole idea of ARIMA model. And then that can be extended to include certain seasonal part. Okay. So here also, if we consider such a dynamic regression model, when we consider this epsilon t part, it is SARIMA PDQ and small PDQ and capital PDQ. The meaning is that if you take the ordinary backward differencing d times, small d times, and the seasonal differencing capital D times, you will come up with something which would be a ordinal SARMA model. So that means no longer this differencing part would be there. So let me explain. So what it is telling you? It is telling me that you take one differencing on this error, backward differencing, then apply another differencing, then apply another differencing. So you keep on doing this. So that actually give you the d times differencing. Now, after doing this small d times differencing, remember that there is also a seasonal part, and that seasonal part also have a capital D. So that means now you have to do, after getting this, you have to apply the seasonal differencing part. And after these many operations, you must be coming up with something, some new time series variable, ut. Now this ut will be following a usual SARMA small p, small q, capital P, capital Q, S, that model. So now the integrated part is gone from the picture. And so this will be the usual ARMA, but with a seasonal component, a seasonal part will be there. Okay. So what we generally do, we don't work with the SARIMA model directly, statistically. We keep on doing differencing on all these variables. And ultimately that will lead to a difference variable, and we do the modeling for the difference variable. So let me explain. So that means you are given this thing. So you can apply a differencing on this YT. Now, if you apply a differencing on YT, that means you are automatically applying differencing on each one of them on the right hand side. Then you apply another differencing, then you apply another differencing. Similarly, you can also keep on doing differencing on the right hand side. So that means if you applied D times this differencing, this will be applied here also. And then you apply this capital D differencing. So that will again be applied on this part, each of this part, okay, like that, and so on. This is the seasonal differencing part. And so now you no longer have the original time series variable, but you have some transformation of that. We call it by the name y prime t. This is the new variable. So after a lot of differencing. So again, this will again give me new variables. So this beta naught part will be gone from the picture, but the remaining variable will be retained, and it will give us beta 1. Maybe you just give a name u1 prime t plus beta 2 u2 prime t, and so on. And finally, this error part, after taking a lot of differencing, we give a name to that, maybe ut, or actually in slide I have given a different name, epsilon prime t. Now see, now this is basically a dynamic regression model, again a dynamic regression model, but this ut follows an ARMA PQ or SARMA PQ. So now this ut follows us. Then you should work with this model. You should apply statistical algorithm to fit this model, and you should do forecasting with that. So that is the idea of this dynamic regression models. Okay. Yeah. So after doing this, all this differencing, actually this won't be there. This beta naught will be going. Whenever you apply differencing, this will be going from the picture, but the rest of the variable will be there. And then you can fit a SARMA model to this equation. So the transform data, and based on that you will get the value of this coefficient, this unknown parameters. So the sole objective of fitting a model to data, observed data, is to identify this unknown parameter, the value of the unknown parameter, the estimate the unknown parameter. Okay, so that is done in this manner. So this is how one can use a dynamic regression model to estimate, to explain the relationship between these variables. Now, once you got some estimated value of this beta 1, beta 2, beta k, you can simply plug in them in the original equation, and then looking into the original equation, you'll be able to say how much this yt, this number of dengue patient, has relation of the first variable, which is the daily temperature. So similarly, you can, while fitting this model here, you can also perform t-test to check whether this beta 1 is significant, this beta 2 is significant, or the beta k is significant or not. But that is exactly equivalent to checking whether this beta 1 is significant in the original model, for the original untransformed data. Like this is the transformed data, this is the original untransformed data. For that, we may have to doing a statistical testing here is same as doing a statistical testing there. So this is how actually it is done. So the statistical package, now in our case, we'll just run some package and it will show us some result. Okay, but inherently what it do, it doesn't work with the original data, but rather transform the data to such a model, SARMA model, and then do the whole statistical fitting procedure, and then get back to the original data. And using that, one can do the forecasting and other thing. Okay. So in generally, maximum likelihood approach is used to fit the model for the transform data. So is it clear how this through this dynamic regression model one can find the relationship of the number of dengue patients with the daily temperature or the daily total rainfall? Okay, so one should not do an ordinary regression, because an ordinary regression will give you inappropriate result. On the other hand, one should definitely do such a dynamic regression in that case. Okay. Yeah, before going into multivariate time series, so we'll talk about another we shall talk about another type of uh, regression model for time series data. This is also called these are called dynamic linear model or DLM. Now for this DLM model, generally these models are fitted uh, using a Bayesian approach. Let me just discuss what a DLM model is. Let us work with a very simple setup first. Now, for the dynamic regression model, we assumed a sophisticated model for this error component. We assume that it is following some SARIMA model, and then we have fitted that to our data to get the estimate of this unknown parameter. However, see that a dynamic regression model is assuming that the relation between the number of dengue patient and the daily temperature, that relation is static in nature. So that means if we are looking into this equation, maybe today, the coefficient that is forming the equation, that value is beta 1. Suppose t is 1. So we are considering today. Now suppose I am considering t is equal to 50. So that means 50 days from today. So that means it is uh, in far future. So there, when I'm looking that this y50, once again I am taking the same equation, like as if I'm considering y1 is equal to beta naught plus beta 1 x1 plus the error on today, the error or the noise part. And when I'm looking into y50, I'm still taking the same equation. I mean, similar looking equation. Now, what I'm assuming that the relation between this y variable and x variable, how that is explained today, that should be explained exactly in the same manner after 49 day or the 50th day. So that may not be correct. That may not give you a good result. So what if we assume that this part, this beta, uh, that is basically determine the relationship between this y and x, that is also changing. So the dynamic linear model actually considers such a setup.
Sir,
Yeah.
does it mean that beta 1 is changing every time for each observation?
Right. Yes, you are absolutely correct.
Okay.
So that means you will no longer consider beta 1, but you will consider beta 1t for that. And then now you have to specify some beta 1t is also a time series, that means, right? And now you have to specify a model for beta 1t. Now, generally what they do, they assume such a model, simple model for beta 1t. So they assume such a model for beta 1. So this model is known as the dynamic uh, the dynamic linear model or DLM model. Now, how do we fit such a DLM model? In generally, this beta 1 0 is assumed to follow something And we have this beta 10 means a particular value. We have this beta naught also. So that is again another parameter. Here we assume, generally we assume that epsilon t follows so in this case, so that means what are the parameters in this model? Like we have 4 parameter. One parameter is the sigma square epsilon. Then we have another unknown parameter, this sigma square eta. Then we have another parameter, the sigma naught square. And we have another parameter, this sigma 1 square. Now what they generally do, I mean, this parameter can be estimated by some classical approach, but typically the dynamic linear model, it is discussed in the context of Bayesian statistics. And the idea of Bayesian statistics is that there they generally don't consider them as unknown parameters, but they consider these unknown parameters also have a probability distribution. Like they assume some distribution for this unknown parameter. Most of the time, they assume some kind of chi-square distribution for them. For the first variable, they consider one chi-square distribution. Those distributions are called prior distribution for the prior distribution for the unknown parameters in the Bayesian model. So they assume prior distribution for all 4 of them, and then they apply Bayesian statistical method to estimate or not really estimate in that case, to come up with the posterior summary or the prediction using this DLM model. So these DLM models are very much used in environmental context, and also they are used in marketing setup. So these DLM models are often used for time series data that contains regression part or the covariates. Okay. So they have been used in such setup quite successful. So this is another type of time series model. Like we have seen the dynamic regression model, and now this is another type of time series regression model, which is called the dynamic linear model. But the first one, dynamic regression model, is generally fitted in the classical statistic framework. This dynamic linear model is fitted in a Bayesian statistical framework. So that's the only difference. Is it okay? Okay. Okay, so this is about when we have one main time series variable, and we have many other time series variables and many other time series which are really not main time series, but they are auxiliary. They are kind of, their role is auxiliary. So we are not interested in forecasting those time series. But what happens, suppose you have multiple time series and all of them are main time series. Like you cannot say one is the main time series and the another one is the auxiliary time series. For example, suppose you have some time series data on the on incomes of individual, or there's some indicator on income of some particular individual, and on you are also measuring the expenditure or maybe average income of an individual and average expenditure. Okay. Now in this case, it is important to predict both the average expenditure, what would going to be the average expenditure of an typical Indian citizen in the coming months or coming years. It is also important to identify what would be the average income of a typical Indian in the coming years. So in that case, that means we are not only interested in forecasting the first time series, which is the average income, we are also interested in forecasting the second time series, which is the average expenditure. So that means we no longer have a primary time series variable and the auxiliary time series variable, but we have two time series variable and both are primary time series. So what to do in such a case? So in that case, we don't talk about time series regression, but they're referred to as multivariate time series data, and we do some kind of different kind of statistical model for this multivariate time series data. Now, suppose we have two times for time series regression problem, we have two time series. One is the primary time series and the auxiliary time series, which is the temperature, and the primary time series is the number of patients. Now, our interest there was in forecasting this YT, but not the auxiliary time series. That means our interest was never to forecast what would be the temperature after 7 days. Okay. Also, in that case, we assume that the relationship is unidirectional, like UT influence YT, but the vice versa is not true. That means the UT influence the YT, but the YT doesn't have an influence over UT. So it is in other way that whether if the temperature is increasing or if the temperature is decreasing too much, there will be definitely the effect will be seen in the number of dengue cases. Okay, but the reverse is not true. Whether dengue cases is rising or declining, based on that, tomorrow's temperature will be increase or decrease. That is not going to happen. So in that case, the relationship was unidirectional. So that is the auxiliary time series, which is the temperature, that influence the primary time series in consideration or the number of dengue patients. But the reverse dependency is not there.
Sir,
Yeah.
Sir, in the second point, our interest is forecasting the YT but not UT. Because in this multivariate time series data, we have both the time series data into considerations. So
Yeah.
why don't we why don't we forecast the UT? Only forecasting YT, why?
In the regression setup, in the time series regression setup. But suppose you not only want to forecast the YT, but you also want to forecast UT. There may be some such setup. We'll talk about a few such examples maybe. So in that case, you want to forecast both of them simultaneously. At the same time, you want to do both forecasting for both of them. So both of them are then primary time series. For example, if you are interested in forecasting in two time series, the first one is the expenditure, monthly expenditure in the coming years for a typical Indian, and the monthly income in the coming years for a typical Indian, like that. So in that case, we are interested in forecasting both of them. So in that case, then we don't use a time series regression model.
Sir, while forecasting the expenditure,
Yeah.
in that case, income would be the secondary interest.
No, actually, in that case, it is a bidirectional relationship. So both the expenditure and income influence each other. Like if your income is more, a typical Indian's income is more, then the expenditure will definitely be influenced. So that is okay, but the reverse relation is also partly true, because if once expenditure is increasing, then he or she will try to switch for a better job with higher pay. So the income will also increase in that case. It is something like that.
Sir, in that case, we cannot apply the multivariate time series analysis.
So in that case, we can apply the multivariate time series analysis, but we cannot apply the time series regression model, where there was a unidirectional relation only.
Okay.
Is it okay?
Okay, sir.
Yeah. So in that case, as we have mentioned that usual time series regression model, they are not going to suffice. So we need something else. Okay. And also we ask a question that what if both y1t has an influence on y2t? So that means it is the cause, y1 is the cause and partial cause, and y2 is a partial effect. Similarly, y2 is also a partial cause and y1 is also a partial effect. So that means there is a bidirectional relationship between y1 and y2 in that case. So such a relationship between two variables, generally they are called a feedback relation. Like y1, if y1 increases, y2 increases. If y2 increases, that eventually push the y1 to increase. So such system are called feedback system, and such a relation is called a feedback relation. Now in that case, we cannot work with a time series regression model, because in time series regression model, the relationship is one directional. Like uh, this yt is the cause and y1 is the effect, something like that. So unidirectional relationship. So that's why in this case, the time series regression model is not going to work, because here we have a bidirectional relationship. And we need models which will treat y1 and y2 equally. But before going into the modeling of this kind of time series, by the way, we refer to such time series data as multivariate time series data, because you have you no longer have a single variable, you have two variable or three variable if needed. So we are considering here two variable, but it can easily be extended to 3, 4 variable, as many variable as you wish or as your data set permits. So that's why we call them multivariate time series data. So you have multiple variable. So in that case, the first thing that we often do, we do some kind of exploratory study, and what we do, we check the relationship between y1 and y2 by something like the sample autocorrelation function. I hope you can recall that there was something called sample autocorrelation function, which check how much y1 variable is dependent with its future. So how today's y1 is dependent with future y1. So how today's number of patient has a relationship with the number of patient that going to occur after 7 days. So those informations were revealed if we look into the sample autocorrelation function. So if the sample autocorrelation function is very high, it is giving you high value. So that means that today's number of patient will have significant effect on even after 7 days, the number of patients that are going to occur. There may be some background scientific explanation for that, but at least from a statistical point of view, today's number of patient has a significant effect on the number of patients that going to appear even after 7 days. Now, such kind of a thing can be devised in this case. These are called sample cross correlation function. Yeah, and this is the notation. I'll explain everything in the next slide. So what it measures? Yeah. So this measure, now see that previously when considering the sample autocorrelation function, we are checking how today's patient, suppose H is 2 or H is lag 1. Suppose H is lag 1. So then what the usual sample autocorrelation function of lag 1 gives you? It gives you how the number of patient on today will has relation with the number of patient on tomorrow. Are they very highly correlated? So that can be, definitely they will be correlated. If today we are expected to get high number of patients, we can expect that tomorrow also very high number of patients will turn up. Okay, so that means there is a high correlation between them. Okay, so that means if you look into the lag 1 autocorrelation for number of patients, so then that would give you some substantially high value. Now the thing is that when you are considering a multivariate time series data, or suppose for example bivariate time series data, then you also have to check such a sample autocorrelation function for the second variable. These are given by okay. So these are given by the sample autocorrelation function for the first variable is given by this, and the sample autocorrelation function for the second variable is given by this. Now, what about this two part? What about this two part? Now, they give the actual cross correlation information. So that means, for example, suppose H is 1. Suppose H is 1. So that what it is telling? That Y2T means today's temperature, and Y1T plus 1, that means tomorrow's number of dengue patient. So that it is this quantity, it is calculating how today's temperature influence tomorrow's number of patient. So are there any correlation? So it check that correlation. On the other hand, this particular coefficient, this particular term in this is a rectangular table of number notation. This is called generally, this is called matrix. Such a notation is called matrix. So in this matrix formulation, this gamma 21H, this actually tells you how today's number of dengue patient will be connected with tomorrow's temperature. Actually, we know that this number of dengue patient has no causal effect on tomorrow's temperature, because it cannot be a cause. Number of patient cannot be a cause based on which the temperature will be increasing or decreasing. It's a completely a climatological process. So number of patient has no effect on temperature as such, but there definitely will be some correlational relationship. I mean, there is no cause effect relation. Like tomorrow's number of patient cannot be the cause of tomorrow's today's number of patient cannot be the cause of tomorrow's temperature. That cannot be possible. But definitely they have a correlation. So there will be some kind of correlational effect, and that correlation will be calculated by this. Now note that this value, and this value may be different. Okay. In this case, whereas this value and this value will actually give me the usual correlation that we already know how to calculate. So this gives you an idea about, so for example, this gamma 1 to H for H positive. H positive, for example, we have discussed for H equal to 1. Now for H, you can also talk about H equal to 2, H equal to 3. So suppose you are considering H equal to 2 or H equal to 3, then what it is telling that how today's temperature will influence the number of dengue patient that would be occurring after 3 days. So it is being calculated by this gamma 1H. Similarly, this gamma 21H, suppose H is equal to 3 or 4, then it is calculating how the number of dengue patient that occurs today or that appears or being admitted today has relation with what would be the temperature after 4 days. It is something like that. So all this information, these are called the correlation across the different time series, like the 2 time series. So that's why these are called cross correlation. So this is the name sample cross correlation function. Sorry, I have written there is a typo. It should be SCCF, sample cross correlation function. Now I give an example of such a bivariate time series data. How would a bivariate time series data, typical bivariate time series data would look like? So we plot the 2 time series side by side, and it look like there is a very high correlation. Like when it is increasing, it is also increasing. When it is decreasing, it is also decreasing. Something like that. So there may be some relation, very clear-cut relation between these 2 time series variable. It is actually a synthetic data, so it may not have any practical real life scientific significance, but it is a synthetic data. But for this synthetic data also, you can see that that 2 time series pattern has some relationship. Like when one variable is increasing, the other variable is also increasing. When it is decreasing, this is also decreasing. So there is clearly some relation between them. So, and our objective is to firstly model this time series together and then do the forecasting jointly, something like that. So that would be our ultimate objective. Okay. So this is the corresponding sample cross correlation function. Like this gives the autocorrelation function for the first variable. This is the autocorrelation function for the second variable. And these are the two cross correlation function as I have discussed. Okay. Now what it is telling, this one is telling that the second variable that this is at lag 0, this is at lag 1, this is at lag 2, this is at lag 3. So it is telling you that the second variable will have an effect up to after 3 days. Like if we look into today's level for the second variable for say temperature, then it will have effect on the number of dengue patients up to 3 days. And beyond 3 days, there is no correlation. So there is no effect beyond 3 days. It's saying something like that. But this will give you just a brief idea how these two time series are correlated, how one is connected with each other. But see, our objective is not just to do exploratory study, but we want to do completely a statistical modeling, and then we want to fit the model, and then we want to do forecasting with that model. So that is the ultimate objective of any time series analysis. So we fit the model, we want to explain the relationship in the model. That is of course an objective, but more importantly, we want to do forecasting, and we want to forecast both the variable at the same time. So that is the ultimate objective for such multivariate time series. So for that, we first have to specify a statistical model. We consider a multivariate version of this autoregressive model. So we have talked about the AR model or autoregressive model. So for multivariate time series data, we'll consider a multivariate version of the AR model. So how would the model look like? So let us first take the first variable or the first process. For the first variable, now how would an AR model look like for the first variable? Only if we have only a single variable. So how would the model look like? So the model would look like this. AR1 model. Now see that in this case, we don't have a single variable, but we have two variables. So what we would like to do, we not only want to include the information of number of patient on the yesterday, but we also want to include the number of not number, but the measured value of temperature on the yesterday. So you also want to include that into the model. So that's why we have an extra term here. So Y1T, today's number of patient, has something to do with yesterday's number of patient plus yesterday's temperature. That is also included. Then this is the error or the noise part. And generally, this is customary to add a deterministic constant value. So that will determine the process level. So this is just this is how it is the convention to propose such an equation. Now this equation look like very much like this AR1 equation, right? But this gives you the equation for the first process. So definitely we have to form such equation for the second process also.
So what is mu1?
Mu1 is like a mean level. So it's like in usual AR model, while considering AR model, we don't have a mean level, but here we have included a mean level. So that is the only difference. Okay. So it's like adding a constant. Okay. So this is customary to include such a constant while working with a multivariate AR model. So it will be a multivariate version of the AR model. Now similarly, we also have such a exactly similar looking equation for the second variable. Now here, unlike just like the previous one, we have a constant level mu1. Now we have a constant level mu2. Recall this. Note that these unknown quantities, this mu1, mu2, they all will be the parameters of our model. And then we have to use statistical method to estimate this unknown parameter of the model. Now this is again another parameter. 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 So these all will be parameters of our model, and we have to use statistical technique or packages to determine these unknown parameters. Now, once again, this equation also includes similar kind of term, but see the difference. These values are now changed. Definitely, this is a different equation, so the value that connects the two variables, they will definitely change. Okay, so that's why we have different notation for all four. This is 511, 512, 521, 522. So in usual AR1, we have only one 5, but now since we have two variable, we cannot work with only one 5, but we have to work with 4 such number 5s. So that's why we will have given such a name 511, 512, 521, 522, like that. And finally, we have a noise part for the second equation, like that. So is it okay? So this model has a name. This is called the multivariate version of AR1 model. This is called VAR model, VAR1 model, vector autoregression model of order 1. We will see the name and these things later. And if we write it in a more mathematically compact form, it can be described in such a matrix formulation. This is called the matrix formulation of the VAR model. We are just writing this two equation in the form of a matrix so that it gives us a compact form. And that can even be written in a even more compact formulation. If we call this y1t, y2t together, we call it bold yt. So note that now I have given a bold face later for denoting this. So this is the custom in mathematics to denote anything that has multiple values. We denote them by bold observation. Similarly, mu1, mu2. Now I am denoting both of them together by a bold mu. Now I have a matrix 511, 512, 521, 522. I'm denoting it by 5 matrix, and now I have made it bold-faced. Similarly, I have y1 t1 minus 1, y2 t1 minus 1. Both of them together, I call them capital Y t1 bold-faced. And finally, I have this z1t, z2t. Both of them together, I call it by the name capital ZT and bold-faced capital Z. So this is the most compact formulation of this vector autoregressive model of order 1. Can you see it looks exactly same as the usual AR1 model? The only thing is that now the thing become bold-faced, because now they are not a single number, but they are like multiple numbers written together. So it looks exactly like the AR1 equation, apart from this mu part. So let us just ignore the mu part. If we ignore the mu part, it would look exactly like the AR1 equation that we have seen in our previous classes. So this is called the vector autoregression model. This is called the vector autoregression model of order 1 or VAR1. We write it in this form, VAR1. Now, just like we have seen AR1 model, and after that we have extended AR1 to AR2 model, similar question may also arise here, that why we are only including the information or that we are assuming that only yesterday's temperature and yesterday's number of patient will influence today's number of patient. Why don't we assume that not only yesterday's temperature, but the day before yesterday's temperature will also have some effect? So if we want to include those kind of terms in our model, then we cannot only make ourselves limited to the VAR1 model, but we have to work with higher order VAR model. So just like we have an autoregressive model of order 1, and that was extended later to autoregressive model of order 2. Similarly, here also we can extend the VAR1 model to VAR2 model, or vector autoregression model of order 2, or vector autoregression model of order lag 2, whatever, order 2, lag 2, same thing. So now the equation would look like bold phi 1, bold face phi 1 yt minus 1, and then bold face phi 2 yt minus 2. Now this YT-1 contained the information of number of patient and temperature for yesterday. Well, YT-2 will include the information on number of patient and temperature for the day before yesterday. It's like that. And in matrix formulation, it would look like this. Now see that previously you have only 4 parameters. Now you got 8 parameters. So that means this is a problem with the VAR model, that if you increase the order of the VAR model, the number of parameter would increase very fast. Like once you increased from 1 to 2, 4 additional parameter would be included in your model. So that's why generally it is better not to work with a VAR model of very high order. But of course, just like AR model and MA model or ARMA model, their order selection was an issue, that how to choose the value of P. I was talking about ARMA PQ. How do we select the P and Q? So there I have stated that although when we'll be using packages or softwares, they will do it automatically, but the underlying concept is that they minimize something called AICC or modified AIC. Similarly also for VAR model also, the order of the VAR model will be automatically returned by the package, and that will be decided by the not by AICC, but for VAR they don't use AICC, because AICC generally give higher order for VAR model, so they use something called BIC. You must have seen the BIC also in last few classes. Like we were talking about, there's 3 things like AIC, AICC, and then BIC. Now for VAR model, they don't work with AICC, but they work with BIC, which is called Bayesian Information Criteria. And in general, when BIC is used, a smaller order VAR model is fitted. Similarly, one can extend the concept of this VAR model, VAR1, VAR2, VAR-P model, where you keep on adding the number of patient information and temperature information, not only for yesterday, but the day before yesterday, the day before that, and so on, like that. And that way you can work with a VAR-P model. But generally, adding too many past information would increase number of parameters in a large amount. Okay. So that's why doing statistics with those kind of model which contain lots of parameters, they may actually give you unreliable results. So that's why it is a better practice to try out VAR model of less order. So in reality, what one should do? One should try out VAR model of order 1, VAR model of order 2, VAR model of order 3, like that, and then take that particular VAR model which has BIC minimum. So that is the logic. That is how you should work with a VAR model. Now, when you use a package which offer you an automatically selecting the order of VAR model, then there you don't have to do anything. You just run the package. You just push a click button and the package will be run. But actually inside the package, they will be doing your task. Like they will be comparing the BIC and returning you the model that matches with the data best in terms of the BIC criteria, the Bayesian information criteria. Okay. So now we just show the result of this VAR model. Just a minute. So this is basically the same data that I have demonstrated there. So this is the original data. Now the thing is that we generally don't directly do VAR model. First we do differencing, and it is the approach is very similar to the dynamic regression model problem. So recall that this dynamic regression model. Yeah. So there I told that instead of directly fitting the SARIMA model, what we do differencing, and after differencing, we fit the model. So the similar kind of strategy is used also for multivariate time series models. So we don't directly use a var model for such time series data, what we do differencing and we make them look stationary. So that means we make them look like something where there is no trend or where the covariance function is rapidly decreasing, something like that. Yeah. So after doing the differencing, the difference time series would look like this. And then if you look into the correlation function, you'll see it is decreasing very rapidly, very fast. Okay. So both this correlation is decreasing very rapidly, and the first variable has some effect. Sorry, the second variable has some effect on the first variable. Like in lag2 also there are some influences, whereas the first variable doesn't have much effect on the second variable, because beyond lag0 there is no influence can be seen in this case. So now here we have fitted a var model to this data, and this is the var prediction it is giving us. So this is the prediction. So what I told you, that the sole objective of this multivariate time series model is to feed a multivariate time series model to the multivariate time series data, and then ultimately do the forecasting. So it is doing that forecasting part. So this is the forecasting value for the first variable, and this is the forecasting value for the second variable. And these are the upper and lower confidence interval for forecast value. Like we have seen that sometimes we are not only interested in point forecast, but we are rather interested in giving an interval that, okay, the future value will be lying within that interval with 95% guarantee. So we give such 95% forecast interval. So the same thing is being given for each of the time series. So now we have two primary time series, and we are doing the interval forecasting for both of them. But that was for the difference data. So from there, I have to go back to the original time series data, and this is how the original time series data forecasting value would look like. So this is how the forecasting value looked like. Okay, so this is so much about this multivariate time series models and their the time series with regression, uh, uh, time series regression model and the multivariate time series model. Now I'll show you how to use some R packages to do this multivariate time series analysis. Can you see the screen, the R screen?
Yes, sir.
Okay, so please open, there was a file called t-series underscore r code 4. So please, all of you, please open that in your R Studio. Have you been able to open that file?
Yes.
Okay. So once you got that file, you have to install a time series package. So go to the install button. So, and search there MTS. So can you see that there is a package called MTS? So you search that package and install in your system. And then we can show you how to do the VAR model, or the how to fit a VAR model to a multivariate time series data. So have you been able to install that? So is everyone getting that file, that package, the MTS package?
Yes, sir.
Okay. So once you have installed that package, then execute the line number 6, and that should load that package in your system. And then execute the line number 7. So that will give us access to the some of the good data sets that are available with that package. So we'll be using one such data set. So just execute the line number 8. So that will be our data set. So what it is giving, it is actually giving us the quarterly information on the GDP of big economies. Yeah. So this is basically starting from 1980 to 2011. So this is the first month, then the 4th month, then the 7th month, and the 10th month. So it is essentially give us quarterly data. It's not monthly data. It is giving us quarterly data for United Kingdom, Canada, and US. So these three big economies. So this is the quarterly GDP data. So then in the line number 9, from this quarterly GDP data, we extract our time series. So you run the line number 9, so that now those month, quarter, those informations are not kept, but only the time series part is kept separately. This is needed for the running the packages, or the running the commands. So this gives you the GDP for UK, the first one, the line number 10. The line number 11 also gives you GDP for and then the line number 3 gives us the GDP for US. So what we do, we take a transformation of the GDP and convert them into the log scale in line number 13. And then we plot the log GDP. Now you see that the scale is much reduced. Previously, you are getting a high value, very high value. So in general, when your data is given in such large scale, you can take a log transformation to convert it back to a scale which is easier to work with. So we often, like population, GDP, these are often converted into log scale because this generally yields very high value. So then this is the log scale GDP for Canada, and line number 16 gives us the log scale GDP for the US. Then in the next step, what we do, as I have mentioned, now we have seen in our slide 2 time series. Now we have 3 time series. So a multivariate time series with 3 variable. The one variable is looking into the GDP for UK. The second variable is looking into the GDP for Canada, and the third variable is looking into the GDP for US. Now, we don't generally, as I have mentioned, we don't generally directly use a VAR model for such multivariate time series data, but I have stated that first we do differencing to make individual time series data uh, uh, behave in such a manner so that there is no trend and the autocorrelation function decays geometrically. So here also you have to do same thing, because uh, the log of even after taking log transformation, the data is growing in a steady manner. Whereas I want a data set where there is no such steady growth. There is no such growth. The growth or the trend part is removed. After doing trend removal, we would like to fit an VAR model. So just it is exactly similar to the univariate time series model. Like if you can remember that in univariate time series model, we generally don't directly go in fitting an ARMA model or ARIMA model. But first initially we determine the trend function, we remove that trend part, we remove the seasonal part. Similarly, such thing also have to be done, or such adjustment also have to be done before fitting a VAR model. So what we do, we take the differencing. And let us see. So this is no longer the log of GDP, but this is after taking log GDP, you take the differencing. Now you'll see that now if you look into the data, that increasing pattern is gone from the data. So no clear-cut trend is present for all the 3 variables. So that means now we can apply the VAR model on it. So what we have done, we have used a VAR model of order 2 here. And this is the fitted model. So this will be the fitted model. So let us try to recall. So we have a term mu1, mu2 in the slides that we have seen. Now, since here we have three variables, so we should have a mu1, mu2, and mu3. So those 3 are parameters. We have to estimate those parameters. So those 3 parameters estimates are given here. So you can see this, right? Estimates first, then estimate second, then estimate third. So these are the parameter estimate related to u1, u2, u3. And then at the second row of that same table, you'll see the corresponding standard error of the estimate, which gives you an idea about the reliability of this estimate. Okay. Then we have seen one phi matrix. If you can remember that there was one phi 1, 1, phi 1, 2, phi 2, 1, phi 2, 2 matrix. So that matrix is given here, this AR1 matrix, this phi 1, 1, phi 1, 2. Now, since there are 3 variables, you will definitely have phi 1, 3. Similarly, you have phi 2, 1, phi 2, 2, phi 2, 3, then phi 3, 1, phi 3, 2, phi 3, 3. And these are the unknown parameters, phi parameters. And since I have some unknown parameters and I have estimated them from the data, so definitely we also have to specify the standard error. So the standard error is given to in the next matrix. So this is the unknown parameter, this is the associated standard error. Now, since we are using an AR2 model, we have another phi matrix. So if you can remember that we have 2 different phi matrices. So initially we started with the AR1 model, the VAR1 model, but now we are looking into the VAR2 model. So we have another such phi matrix. So this is the AR2 matrix. This is the second matrix. So these will be the estimates of individual parameter for the second matrix, and this is the corresponding standard error. Okay. And here you will see that you will get an information on the BIC. That BIC will give you minus 30.726. So by looking into the BIC, so this will give you just BIC for year 2 model, the VAR2 model. Now what one can do, one can try out a VAR3 model, VAR4 model, VAR5 model. So you will try out different models and you will note down the corresponding BICs. And then based on the smallest BIC, you will select your model. So that is the idea. Okay. So here we use BIC to select the appropriate order of the VAR model. Now, once that model is selected, then the next thing that we like to do the forecasting using that VAR model. Now, this is the last line, the 23rd line. That command will execute that. So what I have, so this M1 is the fitted model. Then in the next line, VAR pred. So that means I am predicting with the VAR model. So the meaning of the command is this VAR pred M1. H is 50. So that means H50 means I am predicting for the next 50 quarters. So if you just want to predict for next 10 quarters, you can just change it to 10 and then execute. So you just make it 10 and then execute. So there you will get forecast values for 10 quarters. Can you see that? Okay. So these are the forecast values for the economies. So for the next 10 quarters, the predicted value for the UK is this. This is the predicted value for the next 10 quarters for the Canada. And this is the predicted value for the next 10 quarters for the US. But remember that this is not the original forecast value. This is the forecasted value that we are getting here. That is for the transform data. To get the original forecasted value, what we have to do? We have to do back transformation. For example, we are working with the difference data. So definitely we have to add them up to get the undifference data. But the undifference data also don't give us the GDP, because undifference data was the log GDP. So that means after you get the undifference data, you should not stop there. Then you have to do the exponentiation, the reverse operation of taking logarithm. So that should give you then the GDP, the forecasted GDP for UK for the next 10 quarters. Similarly, it will give the GDP for Canada for next 10 quarters, and similarly, it will give us the GDP for the US for the next 10 quarters. And these are the corresponding standard error or prediction. Unfortunately, for this particular package, for this particular function, they don't give you the prediction interval, but rather they give us only the standard error of prediction. So that will give us an idea about how good the prediction is. Okay. And also it give us the root mean square errors of prediction. So both the standard error of prediction and root mean square error of prediction, they'll give us an idea about how good the prediction is. Actually, root mean square error in prediction is more appropriate to assess the quality of the prediction. So from there, you will be able to judge whether the predicted values are they are reliable or not. So that way, you simultaneously predicted 3 different time series together using a VAR2 model. Okay. So that is the idea that I was supposed to discuss using this R package. So this is where I would like to stop. So if you have any query, you may ask me now.
So taking
Yeah.
the example of dengue with temperature, if my primary interest is not in forecasting the number of dengue cases as the temperature changes, but to find out the association, do I
Hmm.
still have to assume that my error term will follow ARIMA, or is it different?
You should assume your error term follows an ARIMA. Even if you are not interested in forecasting, but
Okay.
still, if you don't assume ARIMA, that means you are doing a simple linear regression type of modeling, but
Yeah.
that won't give a reliable estimate of your coefficients. So maybe I can go back here. Yeah, so the shared screen is visible, right?
Yes, sir.
Yeah, so that means you are basically considering this kind of a setup, but the only thing is that your main objective is not to do forecasting, but exploring the relationship between the variables, something
Yes,
like that. Yeah,
yes.
but then also, if you don't assume ARIMA, if in that case, basically when you don't assume ARIMA, you are assuming this kind of an assumption that the errors are IID, which will definitely give you uh, part estimators which will be poorly performing. So that means whatever estimate you are getting for this unknown parameters, and that will give you an idea about the effect of temperature, effect of humidity, effect of other variables. That may be misleading.
Okay.
On the other hand, if you work with an ARIMA error, you will get better estimate, more accurate, which are more accurate.
All right, sir. Sir, and if my outcome variable follows a Poisson distribution and not a normal distribution, will similar
No,
equation work?
no. In that case, this is not going to work. So this is only when this white is like a normally distributed variable.
Okay. And sir,
Then
can
then
you
then
please?
maybe then maybe you have to suitably transform it so that it looks like a normal distribution. Firstly, that is one option. And if that is not possible, then uh, perhaps you have to use some kind of a GLM. There is a concept called GLM regression, generalized linear model, or Poisson regression. There is something
Yes.
called Poisson regression. So you have to use this kind of a strategy in the context of Poisson regression. That you may have to do. But this model is not going to help you there.
All right, sir. Sir, and
So
can you please demonstrate how to back transform the predictions that we got using VAR model? What will be the R code?
uh, okay. So, what's this? Square eight equal to P1. Yeah, so if you want to do back transformation, what you can do, you can take the exponent, this function exp. So what actually I am doing, I'm just extracting the prediction part.
So your screen is not visible.
Okay. Just a minute. Yeah, so I hope now it is visible, the art screen.
Yes, sir.
So that we have taken the log transformation. So, and then after that, we have got some value. So what we can do, if we want to do the reverse transformation of the log transformation, so suppose I extracted the values. So this actually, this val contains the value, the forecasted value that I have received. And then I can just simply write the x function. So that will convert it back to the opposite direction. The process that was done by the log transformation, it will convert it back to the opposite direction.
And what about the differencing part, sir?
Yeah, the differencing part, perhaps I have to write a small line of code for adding up. So that part would require some part of writing code. I think directly getting a transformation may not be possible. I don't think there is any such direct function available for getting it back. So we have to write a small chunk of code to get it back. So basically we have to add up things, keep on adding up things like that.
Okay, thank you, sir.
Okay.
Thank you, sir. But I do also have a question. Though
Yes,
it is
yes.
a very basic question for statisticians, but like for us medical students, not actually, I'm doing a PhD. So, sir, a very basic thing for
Yeah.
regression.
Yeah.
We need to have the data randomness. For rare diseases where the sampling technique can only be complete enumeration,
Right.
so in that case, um, we can't predict the disease trend by ADIMA model for those rare diseases. Or if there is a chance that we take data from sentinel sites. Sentinel, I guess, you know about sentinel sites, or should I
No.
explain?
Yeah. So please explain. Yeah.
Sentinel sites are places where, suppose in West Bengal, there are 5 to 6 sentinel sites where some specific rare diseases are only screened, because screening for those diseases requires certain infrastructure,
Okay.
which can't be available everywhere. Okay, but there are certain private setups as well where those infrastructures are present.
Right.
So, suppose my topic is on some of the rare diseases. So like if I am doing, I have to do a complete enumeration, because as I said, rare diseases cannot be found in the field, so I have
Right.
to take the hospital data. So I am taking data from a sentinel site. Okay, and I had to do a complete enumeration for that. And if I want to do a ARIMA model for it, since it is a sentinel site, do I need that randomness, or can I do the ARIMA model? Because I think randomness is somewhere hampered, because there are some private places where the
Right. Yes. Actually, the thing is that whenever we do statistical model, we assume lot of idealistic things when we do
Yes.
mathematics. But on the
Yes.
other hand, when in applied work, and like I have worked with some groups of biologists, not in human related subjects, but in other areas of biology. So
Yes.
there also, when they do field research, I mean that randomness is never assured. Okay, but
Yes.
we go ahead with the usual statistical technique, uh, provided uh, some kind of randomness is ensured, but it need not be perfectly a completely randomized setup. I mean that is not possible really. You know.
Okay. So then, sir, since it is a sentinel site where I am taking the data from, so it is the definition of sentinel site says that all the supposed the proposed cases of the rare diseases are going to be screened from that area of that particular district in that sentinel site. So
Okay.
is it possible to do ADIMA model in such a case?
Yes, I think it is possible. I mean, see what would happen at most, the performance of the model may not be as good as an ARIMA model which could have been applied to a completely random idealistic framework, but that is all right. I mean it is still workable.
Okay, okay, sir.
Yeah, it may not give you the best result because definitely
Okay.
certain violations are there, but still,
So
I mean,
do we need to take any error like for sampling? We sometimes take in multi-stage sampling where simple random sampling gets hampered. We usually take design effect. For these cases, should we take any
right,
kind?
right. So in that case, if you it would be a better idea to include such variables which will account for the violation part.
So, what is, sir? If you can just let me know what kind of variable you any x y z variable won't work, na. So
Right.
we need to take a certain variable. So what can that be? Any term, specific term which it has or anything?
Yeah, but right now I really it's difficult to suggest. I mean, if I
Okay,
definitely can suggest if you let me know in detail about the idea. I mean, then
okay,
perhaps
sir.
I
Okay.
can give you some idea. I mean, it may not be the best. I'm not giving the guarantee that it would be best, but yeah, maybe if I know what the problem is and where we have to take into account the this non-violation part, then perhaps I may suggest you something. But
Okay, sir. Okay, sir.
yeah,
Thank you so much. So I'm like expecting to contact you for that, uh,
okay,
and
yeah,
expecting some help from it.
yeah, surely,
So
no problem. Yeah.
okay, so thank you, sir. Any more questions, or should we end up with the session today? And since today is the last session, so any question overall to sir?
Ma'am, one question. It's general one that I have missed day 4 and day 5 session. So if there is recording, if you can provide that now, it will help us to understand it better. Because part of today's lecture that I haven't understood well. So unless I go through day 4 and day 5 now, I won't be able to do much better.
We will talk to our workshop team, and we'll seek permission from sir as well. So if everything, we will let you know through mail whether it can be shared or not. Okay.
Okay, I have mailed also for the same request.
Okay, that will be dealt by the Secretary General and the President, Madam. So we'll let you know soon, earliest.
Yeah, actually, uh, uh, I think it would be a better idea that if we can keep this WhatsApp group for a few days, maybe. Then, if someone has some queries, it may happen that during the class time, perhaps that
So,
question didn't
so the
turn up.
WhatsApp group will be kept, but the sharing or recording the share of recordings and
Okay,
the
that
physics
I understand. Yeah,
that
yeah,
we
that
have to
part is
take a
okay.
decision on.
Yeah, that is. I'm not talking about that, but just
Yes, yeah.
yeah, the group part. Because if someone
Yes,
may
yes,
ask some question,
yes,
maybe.
yes, sir. Yes, sir. We will keep it.
Yeah.
And so there are no questions, or we should end the session today. So I hope we all had a very knowledgeable discussion in the last 6 sessions, and sir has very elaborately and nicely put up the whole thing, and there can be many queries as well. So sir has also asked us to keep the WhatsApp group where you can communicate, we can discuss things there, and the certificates for this workshop will be mailed to you within a month. And sir, anything you want to say to the participants or to IPHA team, anything you wish to say to us?
Yeah, actually, it was really a good experience for me also to work with all of you. Like, yeah, I have never taught so many, uh, uh, so large group of doctors. So it is definitely, I was thinking, how should I proceed? Because it's really not a class on mathematics. But I hope that I have been able to uh, mm, uh, deliver what I supposed to teach you. And also, there was a lot of questions from your side, which was very good. I think that is most important. I mean, so that I get a check on which part maybe I missed, or which part I should think in a different way. So this is a two-way kind of system where I also got benefited by many a question which actually uh, later make me think about some other problems or some other issues of certain models, time series models. So this is really a nice experience for me as well. Like many questions where the data is not available or what we can do. So like these are also learning question for me as well. So thank to all of you being interactive in hybrid mode or in virtual mode. It's generally difficult to keep the attention, but at least I got many critical questions, so I'm sure that at least many of you have followed it very meticulously and for so long. So thank you for that. Yeah.
Thank you, sir. Thank you. It was a really wonderful experience, and we have learned a lot from you. And we expect to just produce more things in research in the coming days from what we have learned from this workshop. So, and we will communicate with you from the IPHA team further for if other classes are needed or other sessions or there are questions or people are asking for things. So, and from our end also, the certificate and other details will be communicated to you also. And the participants, thank you for the attention and what sir said, the questions. So that means you were very attentive, and thank you for your participation wholeheartedly. And so we end up this session. You will be getting your certificates through mail within a month. Thank you, sir, and thank you all the participants on the behalf of IPHA team.